So we've gone over two of the fundamental rules of counting so far, the sum rule and the product rule. And since these two are really the most foundational ones, the basis of everything that we'll be doing, I want to go through a couple more examples. And in particular, I want to give examples of problems where we have to combine both of these rules to get what we want. So here's a nice example that I'm glad to talk about because it's nice because it's actually, let me say a couple words before we start. It corresponds to, it's like a real world thing that people actually care about. So, there was some time when someone actually did this computation and realized that, well, okay, let me give some background. IPv4 refers to the internet protocol. So it's basically how you send things over the internet. And you need addresses to know where to send things. And these addresses are allocated by, some standards body. And there's this big problem that is sort of ongoing, that the original way that people built the internet, there are not enough addresses to support the way, the huge way that the internet has expanded. So the original IPv4 has run out of addresses because they did not make them big and long enough. So this is an actual problem that someone actually, sat down, I think in possibly in 1980, if I remember correctly, was the first time I think that this problem was sort of explicitly talked about, that people realized they were going to run out of IP addresses. And then there have been various proposals and various things to deal with it since. But let's go through this little example. So IPv4 addresses come in basically three categories that I want to talk about. So it's a string of zeros and ones. It's a string of bits. So there are three possibilities. A class A address is a collection of addresses that would be given to a big organization. So it looks like this. It is a 0 followed by a 7-bit net ID followed by a 24-bit host ID. So by a bit, I mean a 1 or a 0. So this is just a string of 7 ones and zeros. This is a string of 24 ones and zeros. And you don't need to care about what any of this stuff means as much, but I want to give some context for it, which is that this is what's identifying the network, and then these are the addresses sort of inside the network. So class A means you have, well, I guess let me defer that for a second so that we can see what we can compare it to. But let me also say that a class A net ID can't be all ones. Okay, so let's do the rest. Class B looks like this, a 1, and then a 0, and then a 14-bit net ID. And then a 16-bit host ID. And a class C address looks like 1, 1, 0, and then a 21-bit net ID. And an 8-bit host ID. Okay, and I said that this class A net ID cannot be all ones, and there is also the restriction that any host ID, in any case, can't be all ones or all zeros. And the question is, how many addresses total? All right, so let me sneak in one more comment for context. Class A is blocks of addresses that you give to big organizations. And what that essentially means is you can see that the net ID, which identifies the network, there are relatively fewer of these than in class B or class C. But this part, the host ID, which is things inside the network, is much bigger, you can see, than class B or class C. So class A is sort of fewer big networks. Class B is sort of in the middle. And class C is like many, many very small networks that you can allocate. Okay, so how many addresses total? Well, like I said, we're going to need to use the sum rule and the product rule to solve this. So there's 3 categories, which is what we think about in the sum rule. And these are the classes, class A, B, C. So each IP address is in one of these classes exactly. It is in one and not more. For example, you can see this because the beginning bits distinguish them. Okay, and then in each class, each has 2 pieces, which are the net ID and the host ID. And each of these is made up of smaller pieces, which are binary digits, which are, of course, bits. All right, so let's build this up. So let's start with class A. So in class A, we have a net ID and a host ID. And the net ID is 7 binary digits. So there are 2 options for each of those things, and 7 of them in this net ID. So that's 2 to the 7. But remember, we also have this restriction that it cannot be all ones. So that eliminates one possibility, and we get 2 to the 7th minus 1 is the number of possible net IDs. And similarly for the host ID, so let's see, how are we going to combine these 2 things? This is a product rule situation, right? Because these are 2 independent pieces of the same object. So we're going to multiply these. And then how many host IDs do we have? Well, we have 24 bits, each of which is a 0 or a 1. So that is 2 to the 24. And we have this restriction that they can't be all 1s and also can't be all 0s. So that eliminates 2 possibilities. So that is all class A addresses. And then for the other classes, we do a similar thing. And then we just need to think about how we combine the different classes. And like we said, this is a sum rule, because each thing corresponds to one class and not the others. Big old plus there. So let's blast through the rest of this. So class B is going to have a 14-bit net ID with no restrictions. That's 2 to the 14. And a 16-bit host ID with the same restriction that eliminates those 2 possibilities. And then class C is going to be 21 bits with no restrictions, times 8 bits with the same restriction that knocks out those 2 possibilities. So this is the number of IP addresses using many product rules as well as a sum rule.